machine learning, artificial intelligence, big data. Everyone wants in, but here's a secret. The best data scientists know behind every powerful model is something far older and far more important: statistics. Get the statistics wrong and the fanciest algorithm in the world will lead you confidently straight off a cliff. This book strips away the jargon and hands you the 50 ideas that actually matter. This is Practical Statistics for Data Scientists. 50 Essential Concepts. ID bot po yesmo opti oki NDs by Peter Bruce and Andrew Bruce, published by O'Reilly. Across 7 big areas, the book builds a working statistical toolkit, exploring your data, understanding sampling and uncertainty, testing your ideas, predicting numbers, classifying outcomes, machine learning, and finding hidden structure. No heavy theory for its own sake. Every concept earns its place by being genuinely useful. Let's walk through the essentials. It all begins with actually looking at your data. Exploratory data analysis. Before any modeling, you summarize. For the center of your data, the mean is the obvious choice, but it's easily dragged around by a few extreme outliers. The median, the middle value, is far more robust. For the spread, you go beyond the standard deviation to percentiles and the interquartile range. And then you plot. Histograms, density curves, and box plots reveal the shape, the skew, and the surprises that raw numbers quietly hide. Good analysis starts with good eyes. Your data is only a sample of a much larger world, so how much can you actually trust it? This is the science of sampling distributions. Here's a beautiful insight. Even when the individual data is messy and skewed, the distribution of sample means tends toward a clean bell curve, the central limit theorem. But you don't need heavy formulas to measure uncertainty. The bootstrap lets you resample your own data thousands of times to see how much your estimate would wobble. From that, you build a confidence interval, an honest range, instead of a single, falsely precise number. How do you know an effect is real and not just luck? Enter the A/B test, the workhorse of the data-driven world. You compare 2 versions and ask, could this difference have happened by chance alone? The p-value tries to answer that, but beware. The book is blunt about how badly p-values get misused. A small p-value does not mean a big or important effect, and statistically significant is not the same as significant in real life. Test enough things at once and some will look impressive purely by accident. Significance testing is a tool, not a magic stamp of truth. Often we want to predict a number, a price, a demand, a risk. The classic tool is linear regression. Fit a line or a plane through your data to capture how the inputs relate to an outcome. But the book draws a sharp line between 2 very different goals. Are you trying to explain how the world works, or simply to predict the next value as accurately as possible? The answer changes everything. Which variables you trust, how you handle correlated predictors, and what the residuals are quietly telling you about where your model breaks down. Sometimes the answer isn't a number, but a category. Spam or not, fraud or legitimate. Will this customer leave or stay? This is classification. Logistic regression gives you a probability, not just a label. But how do you judge how good it is? A single accuracy number can lie, especially when one class is rare. So you read the confusion matrix and you weigh precision against recall, how often your positive predictions are correct versus how many of the real positives you actually catch. The ROC curve and the area beneath it capture that trade-off in one honest picture. Now, the modern toolkit and the book grounds machine learning in statistics, not hype. Nearest neighbors classifies a point simply by looking at the company it keeps. Decision trees split the data into clean readable rules. And then comes the power move. Combine many weak models into one strong one. Bagging averages many trees to cut down variance. That's the random forest. Boosting builds trees in sequence, each one fixing the mistakes of the last. These ensemble methods quietly win a huge share of real-world prediction problems. Sometimes there is no label to predict at all. You simply want to understand the structure hiding inside your data. That's unsupervised learning. Principal component analysis squeezes many correlated variables down to a few key directions that capture most of the variation, turning a tangled cloud of numbers into something you can finally see. And clustering, like k-means, groups similar records together, revealing natural segments, customer types, behavior patterns, anomalies. It's how you discover the questions you didn't even know to ask. But what truly makes this book special isn't the formulas, it's the judgment. Again and again, it warns you of the traps, confusing correlation with causation, p-hacking your way to false discoveries, trusting a model that merely memorized the noise, and forgetting that a sample is only as good as the way it was collected. The data scientist's real skill isn't running the algorithm, it's knowing when to doubt the answer. So, if you're moving from coding into data science or from classical statistics into the messy, real world of data, this book is a rare and valuable bridge. It's practical, it's opinionated, and it's refreshingly honest about uncertainty. 50 concepts, and each one is a tool you'll reach for again and again, long after today's trendiest model has gone out of fashion. Practical statistics for data scientists won't teach you the flashiest neural network. Instead, it does something more durable. It teaches you to think clearly with data, to measure uncertainty, question your results, and tell real signal from random noise. Master these 50 ideas, and every model you build afterward will stand on solid ground. Thanks for watching. If this helped, subscribe and keep reasoning with the data, not against it.